not to give anyone flashbacks to their days in maths class, but if you could all begin by answering the question on the board in your heads, that'd be great. Now, before I get there, I'd like to talk a little bit about why I'm giving this talk. For much of my life, I've loved maths. Not all of it, admittedly, but much of it. I think a large part of this is due to my parents, but also because I've been exposed to a lot of great educational math content, not the least of which involves my teachers. Shout out Ms. McShane and Mr. Lithgow. Now, when I ask my friends about their opinions of the subject, their opinions are somewhat more mixed. And I often wonder why. Maybe they haven't been as lucky as me to appreciate the real joy and beauty that is the subject of maths. To try and fix this, I decided to give this talk today. And hopefully by the end of it, at least one of you is a convert. At least there is one more person in the world who appreciates the beauty of mathematics. Now, going back to the question, what is the biggest number you can think of? If any of you are at all like smart alecky, 10-year-old me, you probably thought of infinity. Maybe even a cheeky infinity plus 1. But what infinity exactly is it that you're thinking of? Is it the number of whole numbers in the universe? How many squares there are? Are these the same thing? Before we get there, we must first understand the idea of cardinality. That simply means a counting of how many things there are in a set. It can be expressed very neatly with this function, written very neatly with n and an a, or whatever the letter that represents your set is in brackets, and it just counts how many things there are. Infinity, however, is notoriously very tricky to count to. I would know. I think I tried once when I was about 8. I got bored at around 600. So to fix this, mathematicians had to switch things up a little bit. So going back to our question, which is greater, the number of squares in the universe or the number of whole numbers? Intuitively, we might think it's the number of whole numbers. After all, if we look from just 1 to 10, we can find 3 square numbers, but 10 whole numbers. Infinity doesn't end at 10, however. Mathematicians solve this problem of comparing infinities by lining up 2 different groups and seeing if there is a one-to-one match between them. If there is, these sets have the same cardinality. And what we see when we line up these 2 sets is that, in fact, they do. Every whole number can be squared to get a whole new square number. This cardinality can be represented by the very neat notation of Aleph 0. Now, this is not to say that all infinities have the same cardinality. Gregor Cantor proved this all the way back in 1891 with his diagonal proof. Say I line up every number from 0 to 1. I then take the first digit from the first, the second digit from the second, and so on and so on. When I'm done with my infinitely long process, I've got a whole new number, which I have not written down, proving that the cardinality of all real numbers is greater than the cardinality of all whole numbers. We now understand a few of the basics of the number infinity. But that's not to say that it was always accepted as an idea. In fact, for a very long time, this was something that was laughable, and mentioning it in any serious math discussion would get you kicked out. All the way back in ancient Greece, the philosopher Zeno proposed what is now known as the dichotomy paradox. Say I want to run a 100-meter race. However, I must first get to the 50-meter mark. Before there, the 25-meter mark, and so on and so on and so on, requiring me to complete an infinite series of tasks, which he held to be impossible. Now, fast forward a little bit, and mathematicians have more or less agreed that infinity does exist. But it's not to say that it is not still very, very weird. The famous Grand Hotel paradox is another example of some of the quirks of infinity. Say you're a concierge who works at the Grand Hotel, the greatest hotel in the world, which happens to have infinite rooms, all of which are booked out. Now, one night, a customer walks in, demanding a room. Not one to turn business away. You simply move the customer in room 1 to room 2, room 2 to room 3, room 2 to room 3 to room 4, and room n to room n plus 1. Congratulations, you've made a little bit more money. Now, just when you're patting yourself on the back, an infinite bus of infinite customers arrives. However, you didn't get this job for nothing. You moved the customer in room 1 to room 2, room 2 to room 4, room 4 to room 8, and room n to room 2n, creating a whole new set of infinite rooms. But, much like Icarus, you have flown too close to the sun, because when a whole new infinite bus arrives with a customer for each infinite real number, you find that you do not have enough rooms to store all of them. But enough with just the mathematics. Let's look at some of the other interesting places infinity pops up. One of these is art, hopefully disproving the idea that maths and art never mix. Fractals are this really cool idea of an infinite shape, which is a single characteristic that gets repeated an infinite number of times. One very famous example of this is the Mandelbrot set. Another very interesting place infinity shows up is in language. Noam Chomsky proposes the idea of recursivity, which is the idea that I can put an infinite number of components into a sentence, and it will still make perfect sense. That might sound a bit weird, so let's think about an example. Say I want to say that the car is red. Hopefully everyone got that. However, I can add more and more information into that sentence. The car which I bought yesterday is red. The car which I bought yesterday and drove around in with my friends in is red. And so on and so on and so on. I can add an infinite number of subclauses, and all of this will make sense. The sentence will still be perfectly grammatically correct. Pretty neat. Now, the last idea I want to talk about is the idea of limits. This, although it might sound like it has nothing to do with infinity, in fact is very closely related. A function is simply something that takes in an input and gives an output. And typically, this input has a range, one that often goes all the way to infinity. Now, as this output gets bigger and bigger, as this input gets bigger and bigger, typically this output converges on a single value, which is just a very fancy way of saying it gets closer and closer to just being a single number. In other words, as the input approaches infinity, the output becomes a single value. Now, this might sound a little weird again, so let's look at another example. What would you say the sum of a half plus a quarter plus an eighth plus a 16th, and on and on and on, what would you say that adds up to? Now, some of you might think it's infinity, but let's look at a very nice geometrical proof of what the actual answer is. Say I have a 1 by 1 square. I take half of the square, and add a quarter, and then an eighth, and then a 16th, and I repeat this process again and again and again. And what I'll find is that I've almost, but just barely missed covering the entire square. What this means, in fact, when we perform a very simple area calculation to find the area of the square is 1, is that this series converges on a value of just 1. So who knew that infinity could be just as difficult to count to as the number 1? But now, despite the impression this might have given you, this is not a maths lecture. And I kind of just want to leave you guys with this idea of a limit. Not as something that is kind of the maximum potential, the ceiling of what you can get to, but instead what happens when you push yourself the furthest you can go, when you reach to infinity and beyond. Thank you.